Okay, let's do an example. The distinction in this example is we're going to start with a coupled set of ODEs. Particularly like this one because I do a lot of work in smart materials where you have field coupling, such as I have a bar and it has a displacement V. It may be coupled with electric field U, and you get things like piezoelectricity. Other cases are shape change under magnetic fields. Another example you're very familiar with is when you heat a material, it will often change its shape through thermal expansion. So there you have coupling between displacement and temperature. So this is really just a toy problem to give you an idea on how would you go about solving those, and is the finite element approach any different when you have a more complex set of ODEs to solve. So we're going to stick with the framework of a 1D model, and we're going to look at a single element between the points x of A and x of B. Ultimately, we want to get the problem in this form. So this is a matrix K. Here is your unknown nodal degrees of freedom, maybe displacement, temperature, electric field, or electric potential, etc. And here are your forces or fluxes. Alright, so here's the first ODE. So just take this as an accepted ODE governing some kind of physical process, and it's coupled to this ODE. The key things to note here are these are material parameters, or a material parameter that varies with respect to length. Here is one dependent variable U, here's your second dependent variable V. So we want to solve for these given some material parameters and given some force distributed over the bar. Same thing down here. Here's material parameters, here's your dependent variable U, here's A again, here's U and V, and you've got this other internal force or flux. And again, here these things are defined. So we put this in the weak form, and the key distinction between this problem and the previous problems is we have to, of course, solve for U and V. So when you do that, we multiply this ODE times a weight function W1, and then for the second equation you have a second weight function W sub 2. Alright, so we apply the same formulation to distribute our derivatives to ultimately get down to a weak form. So down here we have our weak form. We bring down the internal force, and you have boundary conditions. So if you work through these, we're just applying product rule. We're substituting in these relations into this equation, so you get this form. Identical to the last case, except this is a little bit more complex. We do the same thing on the second equation. So here I'm expanding out the product rule. I use this form to substitute back into the weak equation. So here's my integrand, here's my boundary conditions. So we've got two equations in the weak form. Comment on natural boundary conditions for the first equation. So we have this at the endpoints. We can expand this out, and we have these two values at the endpoints. So I'm going to call this P2. I'm going to call this minus P1. We'll get into these differences in sign notation later. This is purely a convention I'm going to use. It'll make sense later, so bear with me. Natural boundary conditions for 2. You apply it the same way. So here at x sub b we have this is q sub 2. This thing is minus q sub 1. And again, I'm using this looks unusual sign convention One example to think about this is go back to the case of a bar with heat transfer, and we're talking about heat flux on both sides. So normally when heat flux goes into a bar, it's positive, but you also got to keep in mind if heat flux is flowing in the positive x direction, it would be positive. If it's in the negative x direction, such as Q1, it's going to be in the negative orientation. So we have to keep track of those things. Again, I'm just giving you this as something to think about now. Reddy talks about this. We'll talk about it more in class. But you do have to be careful with how you define your sign convention. The key, ultimately, you just have to be consistent throughout the whole problem. I could have defined this as positive, but when you do that, you got to make sure through the whole process the mathematics is consistent, and if so, it'll work out. Alright, so remember, we want to find u and v, so we're going to approximate it. So we have these unknown coefficients, u sub j over the element e and v sub j over the element e, and we're going to introduce a function for interpolation between those nodes on the element, and same thing here. For the Galerkin method, we make the weight functions to be identical functions as our interpolation functions. Okay, so that's why I define W1 as phi, W2 as psi. So now we just substitute those relations in. So you notice here's my approximate solution for u, here's v, and keep in mind these are constants. So when I take this derivative, these are just constants, and you only take a derivative on the interpolation function. I've brought down this term as well, and the endpoints. We do the same thing on 2, so I substitute in my interpolation functions, taking the derivative here, and do the same thing on u and v here. So now, remember, we want to get this into a matrix form, right? So let's consider this general form here. I have a summation j to m. I have qij 11 u sub j, and then kij 12 v sub j minus a force, and a similar notation for the second equation. So this is going to represent our first weak form equation. Here's our second weak form equation. So if you do a comparison with these two equations and our weak form from up here, what you'll find is the definition for these matrices, right? So we get these definitions for K22 ij. It's a little more complex. Here's Kij21, and whatever's left over gets lumped into the force equation. If I come back up here, you'll notice we're consistent with our indices. So I have psi I, psi j, psi I, I guess we call this phi j. So these are our off-diagonal terms here, and something similar over here. For 2-1, I get phi, or phi and psi, or psi and phi. Here I get this form for the variable v, and you notice I only have an indice I for f sub I. Same thing here. So this gives you a general form on how we would define these integrals in terms of matrices, the k's and vectors of the unknown constants. Doesn't tell us what the coefficients will be in the matrix. There you have to integrate this out. To do that, you have to have an explicit function for this. We've talked about one form as a linear interpolation. Once you introduce that, then you can integrate that out and get constant coefficients. We'll talk about that next time.